Hey, welcome back to the second modeling talk this morning. It's a pleasure for me to share this with here from London, and he will talk about modeling of cross-linked fiber networks and tissue cell formation.
Okay, thank you very much. I would like to thank the organizers for the invitation. It's a fantastic meeting. I really enjoy the talks, and I learn a lot. I've been working on this problem for a while. This is actually a joint work with my former PhD student, Diane Perisha, who is now in Vienna in the Christian Schmeisser's group, and a colleague from Toulouse. This started when I was still in Toulouse, and then I continued in London. So there's been, I'm mainly going to talk about this paper, which has been published in the recent years, 2016, and this paper, which is still in the process of reviewing. And that's actually part of another a bigger project on the self-organization of adipose tissue. Last meeting in September, I talked about this project to this work, which involves, I would say, more of the biology side of the work. And today I'll rather speak on this work, which is actually how to get a continuum model from this individual base model, and this is going to involve more the mathematical side of the project. So these are the sponsors, and so let's go directly to the goal. So the goal of the project was to understand and try to provide a model or a framework I don't know if you really see it, that's a picture of a adipose tissue of mouse, and what you see is that you have in red you have the adipocytes, which are basically containers of fat, and so these are big balls of fat, and there is a small part of this cytoplasm on the side. These are collagen networks, and you see that the adipocytes are grouped into these structures that are called lobules, and they are surrounded by the fibers. In green, actually, you can see also some of the stem cells, so these pre-adipocytes that eventually will differentiate when there is a need for say energy storage. Okay, so I mean there is a lot of interest in studying adipose tissue for things related to obesity, and also adipose tissue is not only a bad thing, it's also a tissue that has a lot of interesting qualities. It is full of reservoir of immunity system. It's also full of stem cells that can actually differentiate into something different than adipocytes. So they are actually using this tissue for regenerative medicine. It's easily accessible. You can just remove it under the skin and actually put it somewhere else where you need. So it's actually a very interesting tissue. And the group of biologists around Louis Castella here is involved in this kind of things. And so we've been developing a model involving the dynamics of cells and the dynamics of fibers, and our interest was to understand how, if this kind of structure could emerge from simple mechanical feedback, or if there is a need for some organization, some I would say some organizing kind of structure. Okay, and so we have produced this individual base model I showed last time. So I'm just going to quickly show a video of the things that we've done. So that's basically inseminating new adipocytes in a random structure of fibers, and there is a repulsion potential between fibers and cells, and there is the fibers have so these are very small line segments, but they have the possibility to cross-link, and the green stars are actually the cross-links. And yeah, and just by the feedback, the mechanical feedback, you have also non-overlapping constraints between the cells, and all this mechanical interaction actually gives rise to a natural segregation between the cells and the fibers, and on top of that, some of the emerging shapes that we see from these cells actually look like these lobules that we see on the image. So we have done a work trying to quantify this, the analogy with between the simulations and the experiments. I'm not going to speak of that today. I spoke about that last time. What I like to talk today about is rather how you could construct a macroscopic model, because the issue is that if you're running a simulation like that, it may actually take some time, some computer time, and this computer time actually scales badly with the number of fibers and the number of cells, so that if you want to increase the size of the sample and actually simulate the whole tissue organization, that's becoming prohibitive in terms of numerical effort. So the idea would be to construct macroscopic models, and my idea was to try to see this medium as a mixture of two immiscible fluids, one, say, cell fluid and one fiber fluid, okay? And so as a start, we started to think about what kind of model for the fiber fluid, okay? So this is what I'm going to address today. We are currently also working on the cell fluid, and eventually in the future may be able to actually couple the two fluids and be able to recover large-scale structures, I mean on scales much larger than this.
Can I stop you?
Yeah?
Your adipocytes, do they have some kind of internal structure?
No, they're just growing. They're just spheres that grow with a certain rule, and that's it. And they just don't overlap. Okay, there's no internal structure. Yes, so this actually, yeah, I'm not going to go through the literature about these individual base models, because this is not the center of the center part of the talk. But I'd like to address the fact that we are trying to use a simple geometrical object as possible, because what we would like to do is to derive kind of as rigorously as possible the macroscopic models from the microscopic ones. And if you start from two complex objects at the microscopic level, then it becomes even harder to get the continuum model. So we need to start from simple models from the start. All right, so we're going to study the fiber network of the extracellular matrix as a networks of cross-link fibers which have the ability to reorganize. Okay, so the cross-links that I showed in the movie have the ability to disappear or to form. Okay, so and we are going to derive the hierarchy of models from individual base models through kinetic equation to a macroscopic kind of diffusion equation. And the goal, the ultimate goal, is to use it as a component of a model of tissue self-organization, but that's future work. Okay, let me give you a few slides about what's been done before, and I'm not pretending that's exhaustive description, and I'm actually very happy if you have suggestions of other references. There's been quite a lot of work about what's called lattice spring models. That's basically networks of springs, and that's related. And or sometimes you have also beams, and so they can they can stretch or bend. They can actually also twist. And there's been a lot of work on the say rheology or the mechanical response of these networks. And in particular, there's been some work on some interesting phase transitions that occur in these media when you increase the density of beams. You have a bending to stretching phase transition. So when you deform the material, first the material results through resistance against bending, and then when you increase the density of elements, then the mechanical resistance switches to a resistance against stretching. If you, for instance, if you drag the two sides. There's been actually interesting works also on a completely different kind of perspective, which are kind of flocking type models, and this has been done by Alonso. And actually, what we are going to do is actually bear some analogy with this, but the mechanism by which we do the flocking is different. Now, if you go to the continuum models, there's been a lot of continuum mechanics models, which are basically based on either considerations of symmetries or phenomenology. There's been work by the group of Prof and Ioanni in Paris. There's been also, I think I would put in this also category, these works by the Schmeiser group, and we had a talk before about this. About the link between the two levels, the micro to macro, there is a theory that's called the effective medium theory, and it's basically some kind of homogenization theory. But all these works are really, having the perspective of structural mechanics. So it's essentially, elasticity, hyperelasticity, things like that. And we would like to derive the laws of fiber orientation through this work. And maybe in a second step, and we didn't do that so far, but recover the mechanical behavior from this fiber orientation. So really looking at the fiber orientation mechanics. So our network has the possibility to remodel, and so there has been also some work about network remodeling, but basically in relation to interactions with cells, and we've seen a very nice talk this morning about crawling through networks, and some cells, for instance, if you think of this mesenchymal type of movement, these cells reorganize the extracellular matrix around themselves. So they cut some fibers, they create some new fibers, and so on. But here I'm not going to address this question. I'm going to try to see if you have intrinsic remodeling phenomena, how they may influence the mechanical behavior of the fiber medium. I'm not going to say that there are intrinsic mechanism, and so I'm just going to explore if there are some such mechanism, what you could deduce from the mechanical behavior of the fiber medium. So that's the goal. Okay. So let's start with the individual based model. So it's a slight variation from the model I presented last time. So we are considering agents which are just elements of line segments centered at xi, and with an orientation which I described by this unit vector omega I. That's actually a nematic orientation, so actually I identify, if you like, omega I and minus omega I, because I don't care about the polarity. I could have polar fibers, but this is not the case I consider here. As I said, these fibers, these segments have the possibility of cross-linking, and I don't make any hypothesis about the number of cross-link per fibers. Okay, so that's and so there are interaction rules at cross-link. So when there is a cross-link, then the rule is that when there is a cross-link, then the cross-link is maintained. So it should be a constraint, a hard constraint. Actually, we'll change it into a soft constraint, and I'm going to assume that there is a kind of a spring force that maintains this attachment point with this attachment point. Okay, so if these go away, then they will be attracted back together with a spring force. And there is also, and that's actually kind of different from what most of the previous works I've shown, that there is I would suppose that there is an alignment torque which is supposed, so when the two segments cross-link, I'm thinking of that this fiber is getting elongated, but there is a resistance to this makes a long fiber. There should be a resistance to bending, and that resistance to bending is actually encompassed in the in a alignment torque at the crosslink. Okay, so there is an energy related to the bonding energy. There is an energy related to this alignment energy. Yeah.
The bonding energy, is this, do you consider like a torque? So is it at a location of your fiber, so it rotates also, or just pushes them together
So
without any drag?
So what I'm saying for the torque is that actually I'm just saying that there is the angle. So I mean the omega I is a unit vector with angle theta I. So if I use a reference direction, say for instance the horizontal direction, I'm just saying that the theta I and the theta j just want to be the same. So if we're in a situation like that, then it's just going to it's going to rotate about the center. Yeah.
Okay.
Yeah. Okay, so there are other interactions. I suppose that there is an external force to set the system into motion, such as, for instance, the pressure exerted by the surrounding medium could be the pressure exerted by the cells, by the adipocytes in my adipose tissue model, and that's contained in energy W external. There is some noise, so there is an entropic term that accounts for some possibility of that the fibers may randomly change position and change direction, and that could actually account for many things, like for instance if you are in the tissue of a living animal, the animal actually moves, and so the tissue is subject to motion, and that's actually may trigger some random reorientation of the fibers. And finally there is the cross-link dynamics, that I'm supposing that when two fibers intersect, and they are not cross-linked previously, they may actually cross-link. And I also suppose that when two fibers are cross-linked, they may actually remove the cross-link, and all this is ruled by some Poisson processes with certain rates. So I'm going to go into more details of these energies right now. But what I'm doing is that I'm summing up of all these energies, so these such as the restoring force energy, the alignment force energy at the cross. So these two energies are related to the crosslinks, the external potential, the noise. I'm assuming that in between two cross-link linking and unlinking events, the motion of the cells and the orientation of the cells is just a gradient flow in direction of the steepest gradient of this total energy. So it's an overdamped motion with some time constant mu and lambda, and I associate this theta I is just the angle associated with the fiber unit orientation omega I relative to a certain reference direction. Okay, so that's what I'm solving, and let me go in more details about the expressions of these potentials. So so I'm supposing that I want these 2 points to be essentially to be sent back to the same point. So the first thing is that when there is an intersection of the two fibers and then the crosslink is created, the distance between the crosslink and the center of the fibers, which is called Likk and Ljkk. So I assume that when I say I and j, this means that I is less than j. So the idea is that when there is a crosslink that is created between two fibers, it's like a new particle that jumps onto the pair of fibers and attach them. Okay, so I'm going to treat the crosslinks as a second species of particle, and this second species of particles, K, is associates to a pair of fibers, and I is the first one, J is the second one, and by convention I suppose that the number I and J are like this, just not to count the pairs of fiber twice. And when the crosslink is created, it fixes the length between the center of the fiber and the position of the crosslink, and so that's quantity Likk, which is the length of the first crosslink, and this Lj, which is the length of the second crosslink, will be fixed throughout the crosslink lifetime. Okay, so which means that throughout the crosslink lifetime we have these two equations. Okay, so the lengths are not changing, and they are fixed at the time of crosslinking. Okay, of course. Okay, so then when I have this, then the essentially the restoring force will be a restoring force as a function of this distance. I can compute this distance from the center of the fibers and the orientation vector and this length. Okay, so here this point is this one, this point is this one, the distance is the norm between the 2 points, and I assume that there is a potential associated with this crosslink, which is just some restoring force times the distance square. And the total energy of the links is just going to be the sum of the crosslinks of these, the energy stored in each of the crosslinks. Okay, so that's the crosslinking energy. There is the alignment torque, so the same thing. I'm supposing that for the crosslink K and associated fibers I and J, I have a sort of potential energy stored in the bending of the two links, which is proportional to the sine of the sinus of the difference of the angles to some power. And here I will take beta equals 1, so it will be a rather unsmooth force. It's not a harmonic force, but the reason for that is just because it is easier in the analysis later. Okay, so I could, in principle, take any power beta, but I would get some more complexity in the course of the analysis. Okay, and the coefficient in front of this expression is kind of a flexural modulus, is a resistance to bending, right? So the greater the alpha, the more difficult it will be to bend the two fibers. And again, the total energy stored, total bending energy will be the sum of these elementary bending energy at the crosslink sums over the crosslinks. Okay, so that's the bending energy. Okay, so for the external energy, I just supposing that at any given point, any given orientation, I have a certain external potential U, and I sum over the fibers. Okay, so yeah, so that's really things that you could change here at this level. If you model, for instance, the interaction energy with another element like cells, you could do something different. But this is just to fix the ideas. So the entropic term, I will actually construct it like in a way that I borrowed from literature on polymers, where you actually add a kind of an energy which is proportional to, say, the noise times the logarithm of the empirical measure of the particles, but since the empirical measure is sum of deltas, you can't take the log, so you have to regularize this distribution in order to make sense of it. So you take a regularization of the with a regularization factor function zeta n, some kind of Gaussian regularization factor zeta n, and then you construct a kind of a regularized empirical measure. You take the log of this, and then you sum up all these contributions of all the fibers, and then you get an energy, kind of an entropy, kind of energy stored in the noise, in the random motion. Okay, so that's the way we do it. And finally, I have to tell you how we do the linking. We select the cross-linking events. So we're saying that a linking event is possible only if the two fibers are intersecting, which meaning that these two lengths have to be less than half the length of the fiber. And as long as the fibers intersect, they have a probability nu per unit of time that they cross-link, and that's just a constant. And when the link is formed, then the new cross-link particle is created at the link by associating the two fibers corresponding to that cross-link. I fix this length once for all during the cross-link lifetime, and then I go on. Okay, and then once the link is formed, then it has a probability nu d per unit of time to be removed. So there is a certain probability to remove the. So that's basically the model from. I mean, with small variance, that's the model that I use for the fibers in the simulations I've shown right before. So the game is the try we go is try to take this model and try to construct a macroscopic model out of it. Okay, so it's simple, but you see that's already something that's quite involved. So it will involve some simplifications. So let's try to derive a kinetic model. So when deriving a kinetic model through some kind of mean field limit, it usually goes to the definition of empirical measures. So I construct the empirical measure for the fibers, which is a sum of the deltas of in space and in position and orientation located at the position of the particles, scaled by the factor 1/n, when n is the number of fibers. And I also define a empirical measure for the crosslinks. That's going to be a function of two fibers. Okay, so the location of the first fiber and the second fiber, orientation of the first fiber, second fiber, and also the length of the distance where the crosslink is along the fibers, so the L1 and the L2. So I get this. Yeah.
The length of the fiber is fixed.
Yeah. Yeah, it's fixed and uniform. Now that's actually, it's a simplification, but you know it's the. So I get this, and so this guy is essentially this definition is 1/. Okay, I have to symmetrize to get permutation invariance. So I get 1/2 times the number of crosslinks times deltas in this big space, position, angle, length of the first crosslink, position and orientation of the first fiber, length, distance from the center of the fiber to the crosslink for the first fiber, same for the second fiber. This location for the first fiber is, say, the position of the first fiber, the orientation vector of the first fiber, the length distance of the first crosslink to the center of the first fiber, and same for the second fiber. And here I just interchange the role of the first and second fiber to make the distribution symmetric with the permutation invariant. All right, so the goal is to write. So this is formal at this level, and I really don't know if it's doable to do a rigorous thing because of this crosslink empirical measure. I'm not so sure if standard approaches apply, but it would be interesting to look at it. So the idea is I'm going to let the number of fibers and crosslink to infinity by keeping the number of crosslink per fiber fixed, or actually other one. It could be varied, but it has to tend to a finite value. And that ratio, psi, which is the number of crosslink per fibers, is to be fixed. Okay. So I mean, formally, it's clear that the distribution of fiber is going to satisfy an equation like that. So this is basically the overdamped motion in space. This is the overdamped motion in angle. So these two contributions here is the contribution of the external potential to translation motion and rotation motion. These two terms are the contributions of the crosslinks, and not surprisingly, they depend on the crosslink distribution function here. Okay, and these are the contribution of the position and orientation laws. Okay, so now in the contribution of the crosslinks, we have two terms. We have a term which comes from the restoring force, so essentially the maintenance of the crosslinks, which is the term involving the crosslink potential, which is this quadratic potential that tells you that the two positions of the crosslink should join. And then I have a contribution of the alignment torque. Okay, so which occurs only in the second term because the alignment torque only acts on the orientational motion, which is the second term. And so I'm going to split the contribution of the crosslink to the orientation motion in two parts, one corresponding to the, say, maintenance of the crosslink, and one corresponding to the alignment torque. So that's, now I have to provide you with an equation for G. And surprisingly enough, okay, that's formal, but we found that actually we get a closed system, okay? So the equation for G is as follows. So it's essentially a copy paste of the previous equation, except that you have two particles. You have two fibers. So you have an equation for fiber. I mean, you have derivative for the first fiber, and you have a copy of these terms that were involving derivative for the second fibers. Since the length of the crosslinks, the distance of the crosslink to the center of the fiber is fixed, there is no derivative in L. So there is no derivative in L. This term here, the right-hand side, is describe the links creation removal. I'll go back to that later on. But let me comment on this. Okay, so again, you have the external potential that acts here. Okay, and the noise. So here, because I described the noise as something that depends only on the first of the one particle distribution. In fact, there is no noise in itself on the second particle distribution. It's all embedded into this term coming from the first one particle distribution. And the surprising thing is that when you're looking at the crosslink, the interactions of the crosslink, that involves again the same F1 and F2 as before. These integrals over the G, and that involves the F, the denominator. So basically, this is about looking at how the crosslinks influence the crosslink distribution, and we found that actually it's a closed term that doesn't involve any higher order distribution. So you could view the G as a two-fiber distribution correlation between the fibers, and you could think, okay, crosslink will introduce also correlation with three fibers and more, but it turns out that at least formally it looked like we can actually cut out the hierarchy after the two-particle distribution. So we have essentially a model for one particle distribution, that's F, and a two-particle distribution, that's G, and that's cut there, it's closed. So it's a kind of interesting model because it contains correlations, but it contains a natural way to cut the hierarchy of correlations after the two-particle correlations. Okay, so that's I think interesting feature. And the link creation destruction operator is as follows. So you have, when a linking is created, that's okay. You need that to have fibers here, fibers there, and then you need that the crosslink you are going to crosslink. So that term expresses that when I decide to crosslink, I fix the length, the distance between the center of the fiber and the crosslink to the value at the moment of the crosslinking event. So that's what these delta functions mean. So when there is a crosslinking, we increase. So we have a gain term in terms of the crosslink distribution function, and then of course we have a loss term due to unlinking. Okay, due to unlinking. So that's the kinetic model. So we're not going to stop here because it's still quite complicated. So now the idea is that we are going to try to make it, to make a scaling in order to get a macroscopic model. Okay, and so how do we do the scaling? We essentially do a diffusive scaling. So we introduce a parameter epsilon, which basically is the ratio of the small to the large scale. And we scale the position like square root of epsilon and the time like epsilon, so typically a diffusive scaling. We assume that the external potential has a spatial component and an angular component, and the angular component is small compared to the spatial component. We assume that we scale the restoring force like epsilon. That's actually not saying that the restoring force is small. It means that at the microscopic scale it's finite. So we're not making the crosslink force infinite in the large scale limit, which may be questionable, but it turns out that it's a good scale for what we want to get in the end. I'm not saying that these are the only choices, and actually we're exploring other possible scalings that could actually give more relevant macroscopic models, but at least this one is something that gives you something at the end. So we assume that the bending rigidity at crosslink of the flexural modulus is large, so we rescale alpha like alpha over epsilon. And I mean, I think that's the most important and probably also the most questionable assumption, is that we assume that we have a cross-link remodeling frequency which is very large, which means that these cross-link or unlinking frequencies are scaled like 1 over epsilon squared. Okay, so all other parameters are supposed to be order 1. So these are the scaling assumptions that we're making. We are aware that that may not be the the most relevant choice for the biology, but I would consider it as a first step into doing things that are more complicated. So the consequences of this scaling as follows: the fast cross-link remodeling rate implies that this right-hand side of the G equation of the cross-link distribution is 0. Okay, so we have equilibrium between cross-link and unlinking. So that means that I can close the cross-link distribution as being a product of the fiber distribution times this product of deltas, and I can use that ansatz, if you like, to put it into the fiber distribution little f, so that in order to compute the terms f1 and f2, the bigger these forces that are induced by the cross-links, they depend on g, but now I have an expression on g involving little f, so I can put it in f here, and I can get a closed equation for f. But this is not the only thing that we can say. Using these scaling assumptions, we also have that everything that comes from the restoring force is small over the epsilon cubed, whereas because we have bending rigidity which is large, the force that comes from the bending rigidity is actually has terms of higher order. There are order epsilon and epsilon squared, and then there is a remainder which is of the same size as here. But these two terms will have a macroscopic influence in the final result. Okay. So we expect that the bending rigidity terms will have a leading contributions, as well as some other terms such as the noise, the angular noise, because I didn't scale anything about the noise parameters. So this is what we're going to see. Okay. And so we end up with a perturbation problem when we flush everything into the equations. That's written like so. So we have a singularly perturbed problem where we have a leading operator Q of F, which is this form, which is like a collision operator in kinetic theory. And then we have a transport term, which has this form plus a remainder. Okay. So let me look at the collision term. So there is a term which comes from the angular noise here. And there is a term which comes from the leading order of the bending rigidity term here, this capital phi f. And that term has an explicit expression like this. So this is basically the cosine of the distance between the theta and the local fiber mean nematic fiber angle, theta f. This is a mean nematic direction. That's the something that cancels this integral. So f is a distribution of orientation. I define theta f as canceling this. There is a unique solution that cancels this expression. That's called the mean nematic direction. And basically the operator, the alignment operator, says that this is the proportional to the cosine of the twice the difference between the actual angle of the fiber and the mean angle nematic angle. Local mean nematic angle of the fibers around this fiber. So that's the leading order. So essentially what we expect is that there is a kind of an alignment interaction that's due to this bending rigidity, and that there is a disalignment factor due to the noise, and then we expect that we have some kind of balance between the two, and that's going to give us the macroscopic model. Now the transport term is what's remaining. So you have the time operator, you have the influence of the external force, the positional influence of the external force, the orientational influence of the external force. You have a contribution here coming from the second order term of the bending rigidity term. I'm not going to express it. It's a second order operator. It will give rise to also diffusion terms here. Its expression is a bit complicated. I don't want to write it, but this is basically a second order operator in space, and it's involved also in a first order derivative in angle. Okay, so that's contribution, next order contribution of the bending rigidity term. Okay, and you have a contribution to the spatial noise. The orientational noise is in the leading order term, and then you have other terms. All the other terms coming from the cross-link and so on are small order epsilon and will be negligible in the limit. Okay, so this is basically the after I've put in all the scaling argument, I'm going to look at this perturbation problem for the fiber distribution function. Okay, so this is how I'm going to, by letting epsilon, I'm going to go to the macroscopic limit. And so again, I've written again the problem. The problem is to let epsilon go to 0 in this problem. Right, and so as you see, the first thing to see is to characterize. So if you send epsilon to 0, then f epsilon will lie in the null space of this operator Q. And so you have first to characterize what is the null space of this operator Q. And it turns out that these are so-called von Mises distributions. I mean, actually, nematic von Mises distribution around a certain mean orientation theta 0. So these von Mises has this expression. So it's just the exponential of this parameter r that was in the front of the interaction term here. That comes from actually all the parameters I have in the model. That comes from, you know, from the bending rigidity, etc., etc. And you have the mean nematic angle theta 0 here, so this, and then you have a normalizing factor, and the distribution function locally is going to be proportional to that von Mises multiplied by the local density of fibers. So I've plotted here, thanks to Wikipedia, a sketch of the von Mises distribution. That's basically like a Gaussian in the circle. So here it's on minus pi pi. I should actually plot it on minus pi over 2 in this case, because it's a nematic direction. But you see that around the mean orientation theta 0 it's peaked, and actually the larger the r, the more peaked it is. So when r goes to infinity, basically you get a delta, a direct delta at theta 0. On the other hand, when r goes to 0, basically you get a uniform distribution. Okay? And so that's the equilibrium of this Q. It's actually clearly seen, because you see that if you send this bracket to 0, there's basically you get the d theta of the log of f has to be d theta of phi, so f has to be proportional to the exponential of, actually with a plus here, to the exponential of minus phi. Okay, and phi is this, so you know it's very easy to get this formula. That is very important because the von Mises is actually very ubiquitous in when you're dealing with these orientation problems. And in fact, the collision operator that we have here, we can write it in terms of the von Mises distribution. We can just say, if I define a nematic orientation theta 0, I can define the linear operator, which is just this guy. The derivative of the von Mises applies, sorry, missing a d theta here. The derivative of f over the von Mises, so it's a second order operator. I'm missing a d theta here. So I get this operator depending on theta 0, and actually the collision operator, which is nonlinear, is this operator applied when theta 0 is equal to the mean nematic angle of f. Okay, so there is a nonlinearity, but which is just encoded into a moment of f, which is this mean nematic angle defined by this. Okay, but this is very convenient if I can write this expression like this, because we will see that this will help us to understand what's going on for the problem, because you see that now we have this, again, we have characterized these equilibria. These are functions that are proportional to the density, and there is a mean orientation which is an unknown, basically, which is arbitrary, but you have to decide, and you have to find equations for the density and this mean orientation, and you have this singularity. You need actually to find this equation, you need to get rid of this singularity, and one way to do that in kinetic theory is to use what's called collisional invariance. And the collisional invariants usually are related to the conservations of mass, of momentum, and energy. But here we have conservation of mass, but not of momentum. Okay? So we have to find something that replaces what's called collision invariance in kinetic theory. And this is where the concept of generalized collision invariance comes in. This was first proposed in a joint work with Sebastian Moch for the Vikshaker model, but it works here too. So you're going to define something that's associated with a given direction. So just give you given a direction. I'm just considering functions that when I integrate the collision operator, but the linear collision operator with this given direction against psi, I get 0 for all f here that have mean nematic angle equals to that direction theta 0. Okay? So as soon as I define this, I can base, I'm basically in business because I will be able to close my, yeah?
So this definition of generalized collision invariances are strictly related to a particular problem.
Yeah.
This is every time that you have this, the lack of, say, momentum conservation is ubiquitous in biology. But you're saying that any time, in some sense, you should look for things like that.
So what I'm saying is that here, it's easy because in some sense the nonlinearity goes through only one single moment of f. So the definition of the GCI in this case is quite easy. In general, if you think of binary collision operator, you can do the same. It's a bit more complicated. Some work in progress with some colleagues, but you can do the same. Yeah. So if you do that, you see you have a restriction on the possible f. So in fact, if you waive this restriction by duality, then you end up with an equation for psi, which is the following. So psi is a GCI associated with theta 0 if and only if the adjoint, the L2 adjoint of this operator applied to psi is equal to this right-hand side. Okay, this right-hand side is actually something that comes from the definition of the nematic alignment angle. Okay, so once you have this, you can actually, in this case, you can explicitly solve it, and you see that all these guys have this expression that they depend only on two constants, say c and beta. This function has this explicit expression, and essentially you have a two-dimensional family. So if you take c equals 1 and beta equals 0, you recover basically the mass conservation. If you take c equals 0 and beta equals 1, then you get a non-trivial generalized collision invariant, which will give rise to an equation for the mean nematic angle. Okay, so that's basically the idea. So again, so the idea is to find this equation for the density and the mean nematic angle. You take the equation multiplied by the GCI associated with the mean nematic angle of the solution itself. You can always do that, but by definition of the GCI, the integral of that guy against that psi is 0. So you get eventually this equation that is going to give you the macroscopic equation that you're looking for. Again, you make two choices according to the choices of those two constants, either mass or something related. It's not momentum conservation, it's some evolution of the angle. And eventually, you get this. Okay, so here is a little bit complicated because the right-hand side, the operator t, I didn't specify what was the contribution of the bending rigidity term at next order. It's a little bit complicated. But what you can see is that basically it's a system of diffusion equation for the density and the mean nematic angle. So you have, coupling terms with the gradient of rho. You have some, some angular terms. So it's a little bit messy. So what we did when we saw that is that, okay, let's look at a simple situation where I assume that the positional contribution of the external potential is 0. Which means that in this case, rho equals constant is a possible solution. So if I take this constant rho, I can forget about the continuity equation, and I can forget many terms in this, and I get this. Okay, so here is a little bit more simple because what you get is, okay, so you get diffusion in theta, then you get extra off-diagonal terms in the diffusion matrix that are given by this. Omega 0, by the way, is just the vector, unit vector cosine sine, and this is the Hessian, and these double dots are just the contracted product of tensors. So you get basically off-diagonal terms in the diffusion equation. You get first-order, nonlinear first-order terms in the gradients. This is the contribution of the external potential. Okay, so this is basically the equation. So in the few minutes left, I'm going to look a little bit at this model. Okay, so again, so I dropped the zero, I dropped the index 0 in the omega just to make it things simpler. So in fact, you know, all these coefficients, alpha 2, alpha 3, alpha 5, they are actually obtained from the kinetic model. So again, from all the constants I put in the model at the beginning, I get the formula for these guys. And it turns out that if I get a well-posed, I mean, seemingly well-posed kinetic model, then the coefficients that I will get here will lead me to a model which is parabolic. So it looks like well-posed, okay? It's nonlinear, but at least the matrix is parabolic. And in fact, for the stationary case, Diane was able to actually prove existence of solutions, not uniqueness. Existence is a nonlinear. It's nonlinear. Actually, we will see that there is certainly not uniqueness in the case of large applied forces, but there is existence of solutions using standard elliptic theory. Okay, let's look at the numerical solutions. So in fact, you can recast the model in this following form. So you have this Laplacian, then you have cross derivatives involving, actually, you can simplify by using the sine and the cosine of the angles. So these are nonlinear terms. Then this is a term coming from the force. Okay, so we did it, I mean, we did just simple finite differences, Newton methods for solving the nonlinearity, some continuity because it's highly nonlinear. And we use an experimental configuration, which is, it's 2D, but we assume that we have periodic boundary conditions here. Dirichlet boundary condition on the orientation, so we assume the fibers are oriented here like this, and say pi over 4 and minus pi over 4 on the other side. And then you have you apply a potential that tends to actually align in the middle the fibers to the vertical direction. So you see what you would like. So these are the potential and the force. So you see, naturally, with no potential, the fibers would tend to, you know, continuously bend like this. But there is a force that tends them to do like this. So what are they going to do? Probably they are going to bend and then all of a sudden go down. So we will see, and that depends on the intensity of the force. And so that's a typical thing that we get. So first of all, just for the numerical simulation, not comparing with the microscopic model, we just realized that there is buckling, in the sense that if I apply precisely the boundary conditions pi over 4 minus pi over 4, I get fully symmetric solutions. So these are various values of the angle as a function of x for various intensity of the applied force. So you see the largest intensity, you get an excursion of the angle towards pi over 2, and then goes to 0, minus pi over 2 and goes to 0. But as soon as you perturb these boundary condition by very small amount, then you get fully unsymmetric solutions, so either down or up. Okay, so typically it's like a buckling situation, like in structural mechanics, where you compress a material, then at some point it's going to buckle either up or down. And so we recover in this sense a typical behavior of nonlinear elastic media, but it's not an elastic medium because there is some viscosity, viscous behavior involved in the remodeling, right? But there is some influence of nonlinear elasticity. Now let's discuss about how accurate is the von Mises distribution. So typically this is a situation, a simulation, and we did a statistics of the fiber orientation in this region and in this region, and the answer is here. So you have a comparison between the micro and the macro, and you see that the von Mises distribution is a very good approximation of the fiber orientation statistics. All right. So now we did a comparison with the macroscopic model, and so we get mixed results that vary according to the crosslink concentration. Okay, so crosslink concentration is tuned by the ratio of the crosslinking and unlinking frequencies. Okay, so at low crosslink frequency, what we do is we fit the concentration parameter in the von Mises against the simulations. And we use that fitted value of R to compute the solutions of the macroscopic model, and we get a fairly good agreement. So I have some movies I'll show you at the end. However, so that's the large applied potential. However, when we increase the crosslink concentration, that fitting doesn't work. So if we fit the concentration parameter against the simulation and we run the macroscopic model, we don't get a good agreement. So what we did instead is just fitting the we're fitting the R directly on the macroscopic model. So this is a kind of the best value of R in order to get a fitting of the microscopic to the macroscopic simulations. Okay, so this is actually a 10 times higher crosslink concentration. This is 100 times higher crosslinking concentration. So what we can say is that given a situation, we can find a value of R that gives us good results. However, it's not very satisfactory. We have to find this value of R by say model calibration, model fitting. Okay. So we think that the reason of the discrepancy is that although very small, you see in the limit, the influence of the crosslinks, the restoring force is zero, exactly zero in the model, in the macroscopic model. However, when you're applying the discrete model, it's not exactly zero, and that's enough to actually make a rather big discrepancy. But at least we get, say, for some choices of R, we get a very close result. So let me just finish by showing you the some movies. So this is a movie of a low crosslink. So the red dots are here are the crosslinks. So you see here on the sides we fix the fibers. These are our Dirichlet boundary conditions. We apply this potential. So you see the fibers are first aligning to the direction of the applied potential, and then they bend and they get there. And here we are looking at the statistics of orientation. Here we have plotted the von Mises corresponding to the stationary solution, and we see that in the course of the simulation we have a von Mises that slightly goes to the slowly goes to the von Mises of the. So here we are plotting the statistics of the orientation near the axis 0.2. So it's of course the statistics may actually depend. The orientation, the R is a constant, but the orientation may depend on the point. So that's a small value of the crosslink concentration. So a medium value. So you see many more crosslinks here. The density of red points is there. So you see that the concentration parameter depends on the crosslink concentration. So it's actually more crosslinks, more bending rigidity. The von Mises is more narrow. So you can see it here. And again, you see that this von Mises is a very good approximation of the statistics of crosslinks. And finally, the very large crosslink concentration. And again, you have quite good agreement with statistics of orientations. Yeah. So yeah. So I'm finished. Let me just few very short conclusions. So we have derived the hierarchy of individual-based kinetic and macroscopic models for crosslink fibers with alignment interaction at the crosslinks. Here for the kinetic model we have two distributions, that of the fibers and that of the crosslinks, which are coupled, but the system is closed. We have the macroscopic model under fast crosslinking remodeling rate and strong alignment force assumptions. Again, that's can be probably relaxed. The macroscopic model is well posed and it provides a good approximation of the individual based model under certain assumptions. And future works is macroscopic model coupled with, so look at when you couple with the evolution of the rho, which I dropped in the last part, or the density, look at other kinds of scaling limits, analyze the coupled kinetic equations, and maybe that's what's interesting is that I think we can generalize this approach to other kinds of random networks and apply it to the modeling in the biological context, such as trying to get a fluid mixture for fiber and cell fluids. Thank you very much.
what's the regularity of theta in the macroscopic model? Is it does it have to be continuous?
Yes, it's actually some Sobolev. It's in. I don't remember exactly what we get, but it's in some kind of Sobolev spaces. Yeah, it's a diffusion equation, so you expect actually that's going to be very smooth. Yeah, yeah.
And wouldn't the microscopic model not allow for faults where you have for defects where you have an abrupt change of angle?
That's correct. I think that if you assume that the processes that involved in the diffusion are very small, you expect that even the solution being smooth, it might have actually very strong gradients. Yeah. I don't think discontinuities of theta might be allowed by this regularity. The short answer is I don't know.
I just want to know what's the order of magnitude of that R you obtained from the fitting.
It's it's the order of magnitude. So it's a dimensionless parameter because it's in exponential of times the cost. So I think this order of 10.
And does it vary a lot when you change the framework of the simulation?
So essentially, it comes from the balance between the amount of noise and the so essentially the R is the ratio of the strength of the alignment force, here the bending rigidity, and in the denominator the strength of the noise. So the larger bending rigidity, the larger R, the narrower the von Mises, the larger noise, the flatter it is. Okay, so that's basically.
Then maybe one last question.
Yes. So just following up on the previous question. So have you considered doing this on a spherical surface? And would you macroscope? So if everything would have this tendency to align, you would still predict a topological error, right? Would that be something that your macroscopic model would be able to?
You mean X being on a sphere, right?
Yeah.
Yeah. So for this model, no, but my former students, actually, Frouvel and Moch, they have looked not at this model, but at a macroscopic model coming from the Vic-Shack alignment model on the sphere. Yeah, yeah, yeah. So they have looked at this. I don't have it in mind what they found, but yeah, there are other work related to the Vic-Shack model by people like I don't remember the name, in the Marchetti group that has done the Vic-Shack model on the sphere, and they have found topological defects, and they have interesting conclusions, number of defects, the dynamics, and so on. If you're interested,
this would be possible, right?
Yes. Well, yes. In principle, yeah. Yes, absolutely, yeah. Because even though you have a parabric model, then you may have on the sphere you will certainly have defects. Yeah, that's right. So you won't have regularity. That's true. Yeah.
Okay, so I stop only because of lunch. But
Yeah.
thank you very much.
Okay.